Hey, Brent, from
Yeah.
this slide, you could have a question. What's the wind direction? It's gonna
Uh,
be
yeah,
the only,
probably the Bergie is probably the only one that I would trust here.
right. To see one is pointing one direction, one is upwind, one is downwind, and of the main wind direction.
Yeah, I think the only one that's free to yaw in this picture is the Bergie showing a wind from the north.
No.
That's funny. All right, folks are trickling in. Derek, do you remember how many we had register total at the end?
Let me check for you.
Okay, thanks.
$40 registrants.
Okay, great. Hey everyone, we're just watching people come in. Thanks for joining.
Hey Brent,
Yeah.
Is content going to kick off at 1:30?
Is what?
Is like the presentation kicking off at 1:30? Or
It's kicking off soon. We're just
oh, okay,
waiting for people to come in.
okay. I think I misunderstood your message earlier, but sounds good.
Okay, sorry. Christine, let me try allowing you to yeah, let's see. Remove, I think you have permission to unmute, Christine.
Oh, hello.
Hi, I can kind of hear you. Oh,
Great.
yeah, hi. Did you have something, Christine?
Oh, no, just saying hi.
Okay,
Do I have
yeah.
my hand up?
Yeah, you had your hand up, so just want to make sure.
Ooh.
But thanks for trying or showing us that that works. Let's see, where's everyone see the raise hand button? It's different when you're showing the screen. Good afternoon, Todd. I see the chat. Great. Making sure all the things work here. Yeah, we had 40 registers, so we're just giving a little time for folks to come in, and then we'll get started in just a couple of minutes here. Thanks for your patience. I'm in, I work remotely out of North Carolina, and we're getting tons of rain. It's all the rage is the rain, the big news of the day. About I don't know, a foot of rain is falling. It's kind of crazy.
Has it been dry though until now, Brent?
Yeah, I mean, it's been pretty dry. Yeah, but this is too much
It's too
rain.
much. Yeah.
Yeah. Tropical storm Helene is causing some influence. Okay, well, let's go ahead and get this thing started. Thanks all for joining. This is the webinar for the Distributed Wind Aerolastic Modeling project that NREL and Sandia Labs have been working on for the past couple of years. We call it dWAM. And we just wanted to take the opportunity to inform everyone some results of the project so far. So thanks for joining. We're going to record the webinar. We are recording the webinar for folks that couldn't make it today. And when we get to Q&A, or if you ever have a question, the best thing to do to get our attention is to raise your hand, and then we'll make sure you're allowed to unmute and let us know what you need. So I'm Brent Somerville. I'm the PI for this project at NREL, and I'm joined with my co-PI, Kevin Moore from Sandia. You want to say hey, Kevin?
Yeah, it's great to be here. Yeah, it's exciting work we're doing. We're glad for the opportunity to present here.
Okay, let's just get through this. So the team, we've got a bunch of folks working on this on the NREL side. You maybe know Jason Yonkman, he's kind of a senior advisor, and Faisal and Abinit work together with Pietro, and Derek and Soria work together on the ACDC task, and Hannah, Andy, and Kevin are working on VOTS, and then Jeroen and Scott are, and about 4 research techs are helping with some field work that's really cranking up this coming next year. And we've subcontracted with Rick and Dean, Rick Damiani and Dean Davis, for some great work contributing to this project. We contracted with Robert Preuss for a workshop we did last year. And then Dr. David Wood and Mohammed Hammam have really, they came in really early in the project with great research around tail vane controlled turbines and a mathematical model of tail vane behavior that allowed us to do some improvements in OpenFast. And then really working closely with OEM partners in the distributed wind industry, Berge, QED, EOCycle turbines have been installed at NREL and will serve as a basis of some validation and served as the basis of some new reference turbines that we've created. Pika is no longer, but we had a Pika, so we did a little bit of work with the old Pika folks, but XFlow has been a big partner in the VOT modeling world, and we're hoping to work closer with Carter in the coming year on their turbine modeling, because we've got some modeling in both bladed and OpenFast that we can do some comparisons on. So an overview of this project, aerolastic modeling is the go-to design method for wind turbines these days, and we saw that the tools were challenging for the distributed wind industry to use. So folks were using other methods or older legacy tools, or paying for tools from afar, or not using them at all. So we did a project with Rick and Dean in 2022, where they studied the research needs in this area. And we really started with a webinar where we brought the modeling community together and talked about where the needs are in this space. And they wrote a nice report that I can put in the link in a minute, that helped us identify the top needs of distributed wind archetypes. And the outcome is that we're trying to advance the design and certification of distributed wind turbines by enabling the aerolastic modeling tools to be as up to date as possible. So distributed wind is wind turbines of any size in a distributed on-site application, but we found out that the modeling tools such as OpenFast were really well suited for large turbine archetypes, 3-blade, upwind, pitch regulated, but some of the distributed wind archetypes in the small and medium scale were kind of left behind, and had some of the capabilities had disappeared as OpenFast and other tools have evolved. So the top archetypes that we looked at in distributed wind were, upwind stall controlled with active yaw, upwind stall controlled with passive yaw with or without a tail, and then downwind stall controlled passive yaw, and then VOTs, looking at the Darius and the straight blade HVOT archetypes. So we focused on those dominant archetypes and saw, looked at the tools to see what was needed to model these turbines. So the tools needed improvement, improved physics for these archetypes, including passive yaw and tail vane control, and of course VOTs. Have had modeling needs for quite a while. So it's really great to have some support to turn the team of modeling experts' attention toward these distributed wind archetypes for a period of time here to sort of do a little catch up on the tools. And another thing that came out of the workshop was that, you know, generating Campbell diagrams is really useful in avoiding the dynamic issues, and that was an arduous task in the tools. So we wanted to invest some time into trying to automate that process. Also, you know, Rick and Dean looked to see what model templates were out there for folks to use as they start the process of modeling their turbine archetype. And there were some that were dated and some that were missing. So we decided to create new reference turbines based on the top archetypes to serve as a platform for research and a starting point for modeling turbines of those archetypes. And then we're planning to use some research turbine data to validate the new capabilities and do a little verification between different codes to also do some checking there. To improve the usability of this new code capabilities, you know, we're putting out a design load basis guidance to help start or initiate the process of modeling your turbine, improve the documentation of OpenFAST and OWINs, and put out, you know, very specific scripts and guidance for distributed wind turbines. And as well as new tools. So the impacts here would be turbines can use the latest tools to have modern engineering applied to their designs, resulting in an optimized wind turbine that's able to be certified in our quest to have reliable, cost-effective turbines on the market. So we're going to go through this agenda. We'll hear from Rick and Abinit on the passive yaw code and OpenFAST improvements, and then a reference turbine update, and then Derek on the AC/DC tool, Kevin, Hannah, and Andy on VOT modeling, Rick on the design load basis guidance document, and then a little bit about what's planning to be to occur next, followed by Q&A. Okay, so I'm going to stop sharing and then turn it over to Rick to start with the new passive yaw friction code in the code, in the OpenFAST code. So thank you for tolerating me, and thanks for being here. Again, we're recording, and if you need our attention, raise your hand, and we'll call on you. Thank you very much.
Can you guys see the screen?
Yeah, it looks good, Rick.
Okay, great. So just I want to remind folks that this work was also authored by Kevin Fletcher, who is a graduate student at the University of Virginia, and he is finishing up his PhD and will probably join us again at the Floating Wind Technology Company, which is this company that we have with Dean and Max and a few other junior engineers that work on a number of different things, including distributed wind. Just a few words about the motivation of this study on the yaw friction. This is the table of contents of the presentation. We'll go pretty quick through it. We'll talk about the motivation. I will give a summary of the theory, and then maybe some snapshots of canonical cases for verification, including a case for a downwind turbine, and some conclusions, potential work to come. I guess I probably should start the video so you can see me as well. So the motivation, just like Brent summarized earlier, we carried out a study in the year 2021 and 2022 that was looking at aerolastic modeling needs for the distributed scale wind turbines, and the yaw friction modeling was part of the top 10. In fact, it was in the top 5, as you can see here. This is the result of an investigation that we carried out across numerous stakeholders, and that report goes into more details about that. We also personally noticed discrepancies in the yaw response in the field and in the modeling for some specific turbines in the 50 to 220, 225 kilowatt range with pre-yawing capabilities. We saw that there was discrepancy, and at times also these machines would settle in a steady state at an angle that was not what we calculated being the wind direction angle. Also, while I was at NREL and I was designing a rotary for Hitachi, which is a downwind turbine, at the time we were looking at a 10 megawatt rotor. And one of the features that this turbine had was the capability of slipping in yaw under extreme wind conditions. It was a feature, but in other machines, obviously that can happen, unplanned. So having a good model for yaw friction could be certainly useful to understand the dynamics and the loads on different kinds of machines, not just distributed wind turbines. So just a few words about the theory. We implemented a basic Coulomb friction and an expansion of that theory for the inclusion of viscous friction. So in the Coulomb friction, as you may very well know, we usually refer to static and dynamic friction, and the Coulomb theory assumes 2 different values for the friction coefficients, and therefore we have different thresholds to use in case the joint is actually static or is moving, so it's in a dynamic situation. And the viscous friction adds a dependency on the speed. It can be linear, but it can also be more complicated. So quadratic, for example, to simulate more complicated joints, not just sliding surfaces, but potentially also roller bearings, for example. So what you see here are just the equations. I'm not going to go into these details, but this is just to give you an idea of what went into the code in OpenFast. We changed the Elastodyne module of OpenFast to include this model for yaw friction, and we also changed the input file to Elastodyne to account for the modality or the various modalities that we can use for the modeling of yaw friction. And so you can see here are the main parameters that can be introduced into the code. And the first one is a flag that allows the user to select whether or not the yaw friction is enabled and whether or not you want to use your own parameters in terms of maximum Coulomb friction torque, for example, and dynamic friction moment at null yaw rate, or if you want the code to estimate what those values should be given a certain static and dynamic coefficient. So in that case, the code would also account for the effect of the normal or axial loading on the RNA. And then, of course, there's a viscous friction coefficient that you can also use. I just want to highlight that by changing that initial flag, again, you can select which model or submodel you're going to use, and you can also augment the entire yaw friction modeling with your own user-defined model. Like I said, a few snapshots about the canonical cases. We started with a very simple case. We looked at an AOC wind turbine, which is a free yawing downwind turbine, for which we have an aerolastic model available. And it's an older machine. It's not used anymore, but it's a 50 kilowatt machine that has, again, an aerolastic model available and publicly available. You can see that it has a 15-meter rotor diameter, and generally speaking, it was mounted on a hub height of 25 meters. So what we did, we turned off all the other degrees of freedom, allowing just for the yaw degree of freedom in open fast, and we adjusted the friction coefficients to verify that we could keep the machine at a certain angle, and we wanted to demonstrate that we could replicate basically the forcing from the aerodynamic integral of all the forces, so that we could replicate that torque coming from the aerodynamics in our yaw model, so we could keep the rotor at a certain angle. So we did that by first disabling actually the yaw degree of freedom, calculating the aerodynamic torque on the RNA, and then allowing the yaw degree of freedom free, such that we could then verify that indeed the yaw friction was exactly opposite to the forcing. Then we went a little bit more into more complicated cases. In this particular case, as illustrated here, we just drove the torque on the RNA to tower joint, so at the yaw bearing, with a prescribed law, and that allowed us also to verify that certain behavior was happening when we would cross those thresholds, again, of static and dynamic friction in particular. And everything turned out to be what we expected after a few iterations and a few bugs that we had to fix. Here's another case where we had a simple decay. We introduced a yaw spring in the machine, and we preloaded it with a certain yaw angle, and then we would expect the yaw to go back to zero or close to zero, depending on how much friction we input. And we verified that with the chosen, again, friction parameters, we would get as a steady state value for the yaw exactly what we would expect for the balance of that torque spring that we introduced. And then we also looked at the verification against servodyne, where yaw damping can be inserted somewhat separately from this module. Obviously, this module can take care of linear damping, as I described before. So we wanted to verify that indeed using using servodyne and the yaw damping in there, or our yaw module in elastodyne would return the same response. And you can see basically these curves here showing the yaw as a function of time. That for these, the curves are basically coincident. Then we looked at also tower-based moments. As you can imagine, if we have friction, we transfer some of that torque. So that is expected. You see here in this lower left plot, in blue, we have the case with no friction, and then we activate friction, and the response is given here in red. And the fore-aft bending moment at tower base is not affected very much, and you probably would expect that. But the side-to-side actually has quite a bit of an impact in there. So this is obviously repercussions, say, on fatigue calculations. So, and therefore, the overall verification of the various components. So again, if you look at the yaw rate, you can see that that is suppressed by friction. So there's obviously damping in there. So this is something that we were pretty happy to discover. So concluding, we implemented a yaw friction that can obviously be further expanded. It's already versatile enough where you can introduce your own formulas if you have, say, formulas from a ball bearing or roller bearing manufacturer. You can try and introduce those laws in there if they are at least describable with equations that are similar to what we already have, or you can introduce your own module within the user-defined function. So this preliminary verification has been completed. We obviously would like to do some more validation against some field data. One thing to note is that those equations are relatively simple, but once implemented into OpenFast, because of the way Elastodyne and Keynes' method was implemented, they become much more complicated. And so at the moment, the high-speed shaft brake torque and the yaw friction torque are calculated sequentially, again, because of this implementation scheme, and that might have consequences in cases where, for example, you're simulating maybe an emergency shutdown with a free yawing machine. In most cases, you shouldn't have any problems, but there could be some cases where this can affect the results. So in the future, this could be fixed. So with this, I thank you, Brent and NREL, for your support, and DOE also for the support throughout this study. And I'll pass it back to you, or if there are questions, I'm available.
Great, thank you, Rick. So in questions, we have Q&A reserved for the end, but if you have any questions as we go along, don't hesitate to bring them up. But we do want to get through all this content. Thank you, Rick. We'll go now to Abinit to switch over to tail vane modeling.
All right, let me share my screen here. All right, can you see the full screen?
Yes, thank you.
Okay,
Oh,
perfect.
no, not yet. We're looking at the presenter view.
Oh, okay.
Sorry.
How
There you
about now?
That's it. Yep.
Okay, awesome. All right, so I guess like another part of this, the distributed wind work was to enhance the tool set of OpenFast, and like Rick just presented the yaw friction model, and I'm going to present the tail fin aerodynamics model. I think like this is not my work. This is implemented by, I think like this is developed by other people, and I just helped implement this model in OpenFast. So we have like two new aerodynamics model in OpenFast. The first one is a steady aerodynamics model, and the second is an unsteady aerodynamics model. The steady model is from the legacy Fast V7 model of the old, but it was not available in OpenFast, and distributed wind turbines, I think like they needed a tail fin model, and the steady model is very helpful in rapid prototyping or design and analysis and stuff like that. Now, the steady tail fin model is a simple polar-based tail fin model. It utilizes a polar lookup table, the airfoil polars lookup table, and it provides users the capability to implement the tail fin as a simple airfoil, and users can provide the lift, drag, and the moment coefficients, and OpenFast can calculate the tail fin forces and moments and the effect on yaw and the entire effect of tail fin aerodynamics. This simple model can be implemented as a separate tail fin aerodynamics input file. As you can see that in this implementation, you can select between the, having like a no tail fin model, a polar based, which is what I'm talking about right now, and the unsteady model, which is the next half of this project, of this presentation. Then the user needs to define the tail fin chord, the area, and the undeflected position of the tail fin. That's basically the arm length in X, Y, and Z direction. And we also provide for the capability of having a tail fin which has a skew, tilt, or a bank angle implemented in there. And finally, this induced velocity model, you can either have like no induced velocity or the rotor average induced velocity on tail fins. And then finally, users can provide the index or the identification of the tail fin file. And that's how this simple model works. Again, this is very similar to how the loads on blades are calculated for a simple steady model. This is, I think, something similar, but for the tail fin, and it takes into account the arm length and calculates all the forces and moments accordingly. And again, this was in the old fast V7 model, but it was missing since we switched to open fast. So this was brought back. I think like the majority of the work here was implemented by Emmanuel, who has left NREL, but yeah, that's what this is from. And the second model that we have implemented is the unsteady model. Now this model is, the theory is developed by Mohammed Hammam and David Wood. And the implementation and like we've implemented this in OpenFast. Now this model is based on unsteady slender body theory. Unsteady slender body theory. It is linearized, but it has been extended to include some of the turbine specific needs, which I'm going to talk about next. So again, like this is the well-known unsteady slender body theory, but it has been extended to capture the effect of, I'm sorry, I think that's going to be the next slide. Yeah, it has been extended to capture the effects of high yaw angles. And this is done by modeling the associated nonlinear vortex dynamics. So this model captures the vortex, the leading edge vortices and how they break down over the chord. This model has also been extended to include the effect of high aspect ratios. So this model includes the distribution of the load in the chord-wise direction, which I think the linear unsteady slender body theory does not. And we can also take into account the time varying nature of the wind. And again, all this, the theory behind this model is explained in the report by Hammam and Wood and Somerville in this NREL report. But we also have a couple of more publications that have been accepted, but they're going to be like available to public in the near future. And that contains experimental validations and even stuff like how do you use experimental data to obtain the coefficients using system identification and other details. So I think there's a lot that's going on behind the scenes here, but like I'm not going to go into the theory in much details, but I'll talk about the implementation in OpenFast from a user perspective. Yeah, so I think like the main equation that has been implemented in OpenFast can be shown like this. Again, like we don't need to go into the details here, but the important thing to note here is that we have like three different terms. The first one, as you can see, is a multiplier. We have like something that are getting multiplied to KP. The second term is KV, and the last term is CDC. So the first term, KP, captures the effect of potential flow on the tail fin. The second term, which includes KV, captures the effect of vortices. So like the effect of vortices on the tail fin force. And the last term captures the effect of the drag. So all of these terms are taken into account. And as you can see, all of these are multiplied by something called a separation function, x1, x2, and x3. These three functions sort of tell OpenFast the relative contribution from the three terms. So, you know, x1, x2, and x3, they act like weights for the potential flow source of the tail fin force, the vortex source of the tail fin force, and the drag source of the tail fin force. Now, these separation functions, they are usually a time-varying phenomena, but you know, Hammam and Wood, they conducted some studies and they found out that a quasi-steady approximation of the separation function is also quite good. So in OpenFast, a quasi-steady approximation of the separation functions are implemented. And you know, I'll just go in a little bit of details of how these separation functions act like. So this is the equation for the separation function, and you'll see that it has a certain parameter called alpha star and a certain parameter called sigma. So these are the empirical constants that characterize the decay of the separation function with respect to angle of attack. And if you can see the equation on the plot on the right, you'll see that alpha star sort of characterizes the angle below which the separation function is quite active and after which the separation functions become deactive. So this alpha star sort of tells us, this parameter tells us what is the value of the angle of attack above or below which the potential flow or the vortex flow or like drag coefficients become important or not. So that's like one parameter that we need to find out. And the other ones are like sigma and so sigma characterizes the slope of this function. And again, like these are the parameters that users need to provide to implement the unsteady slender body theory based model. And as you can see, xi takes a value between 0 and 1. So they sort of, act as weighing functions. Again, and I'm not like going into the implementation of this part here, but the report goes into much more details in how to find the values of these parameters for different set of tail fin tail fin sections. So we have like specific formulas for simple plan forms like elliptical wing or delta wing, and even we have I guess like suggestions on how to find these coefficients for a more like a complex wing where the shape of the tail fin is it can be like a concave, it can be a non-convex shape. So all of these details are given in the report, but this is like the broad overview of how this unsteady slender body theory based model works. And again, like to implement this model in OpenFast, all the user needs to provide are these coefficients, this snapshot of the tail fin aerodynamic input file. As you can see in the slender body section, the user needs to provide the value of the Kp, Kv, and CDC. These are like simple constants. And then the three angles of attack that correspond to the potential flow, the vortex flow, and the drag coefficients, and the corresponding sigmas, which is the parameter that defines the slope of the separation function. And the rest of the data is pretty simple: the tail fin area, the tail fin positions and angles, and stuff like that. And again, like this model has been implemented and tested experimentally as well. And that's a separate publication that we have. And again, like all the credit of developing this theory goes to Hammam and Wood. And yeah, we have this implementation that has been tested. So I think like this is something that is like very useful if the user needs to implement something that is higher fidelity compared to a simple vortex polar based approach. Yep, that's it.
Excellent. Thank you, Abinit.
Yep.
Any questions on that before we move to, we keep Abinit and move to the reference turbines? Great. Well, as you can see, the team's been busy putting back old code and then putting in fresh new code for some passive yaw archetypes into OpenFast. So thanks for all the work that was done there. And some of that work was immediately used to create 3 reference turbines representing 3 different archetypes of distributed wind turbines. So Abinit will go through the status of those now. So thank you, Abinit.
All right. Let me just change the presentation and share my screen one more time. Give me a second here. Oops. All right, can you see the full screen presentation again? Yeah.
Yes, looks great. Thank you.
Okay, awesome. So yeah, I guess like this is the second like another part of the project where as Brent's and team suggested that in their previous study they found that there are like several things that were lacking in terms of like the current state of the aeroelastic modeling of distributed wind turbines. And one of the suggestions that they came up with in the previous seminar was that we need to have simple, reference turbines for distributed wind energy systems, same way that we have it for large wind turbines that represent like different archetypes, and that can help in the aeroelastic modeling of these sort of turbines. So the three archetypes that are being developed under dWAM are a 15 kilowatt passive yaw upwind turbine, a 90 kilowatt passive yaw downwind turbine, and a 20 kilowatt active yaw upwind turbine. And these three turbines, these are based on existing industry standard turbines. So the archetype A, which is the passive yaw upwind turbine, is based on the Berge XL15 wind turbine, while the passive yaw downstream turbine is based on the EO-cycle Phoenix 20 turbine, while the active yaw upwind turbine is based on the QED Phoenix 20 turbine. Now, internally, we have also developed an aeroelastic model of the Pica turbine, but that's going to be, for testing, and we have this turbine installed in the Flatirons campus. So we're going to use that model for internal testing and validation of the tail fin model and stuff like that. As you can see, it has like a very interesting tail fin planform. So yeah, but like the three reference turbines that will be publicly available are the first three. So I'm going to first talk about the NREL 15 kilowatt turbine. And again, like there's like a lot of information here, so I'm like going to go a little bit faster here to like only talk about things that are of interest to this audience here. So like this turbine is a 9.6 meter rotor diameter turbine, and it has a rated power of 15 kilowatt and the rated rotor speed of 150 RPM. As I said, this turbine is passive yaw and upwind. And again, like all these turbines, they do not have a pitch actuator. So they are all fixed pitch turbines. Here are the details of the structural properties of the blades. And as you can see, the flap-wise and edge-wise stiffness distributions are shown, as well as the mass density distribution. And the mode shapes and flap-wise and edge-wise mode shapes are as expected. And we have full details of the aeroelastic model, including the mass, the first moment, second moment of inertia, and center of mass. We assume that like all these modes have a structural damping of 0.47% of the critical value. Yeah, so that's the structural properties of the blade. If we go to the aerodynamics properties, we implemented the blades using two open stall regulated airfoils that were developed by NREL like long back in the 90s. And these are the S822 and S823 airfoils. And as you can see, like the airfoil polars are calculated and provided with this model. And yeah, the blade chord and the blade twist profiles are also provided. But I guess the main thing here is that we are using publicly available open source airfoils for this model that was developed by NREL for distributed wind applications. The tower itself is a simple cylindrical monopile tower, with a constant diameter of 1 meters. And we have the distributions of mass density and stiffness. And of course, it's a cylindrical tower, so the side to side and fore aft stiffnesses are the same. And this model also has a tail fin. The steady tail fin aerodynamics code has been implemented with this model, and the tail fin has an area of a chord of 0.5 meter and the area of around like 1 meter square. and the moment arm is 3.3, but you can see that the tail fin has a tilt of -8 degrees, and the tail fin polars are provided with this model as well. Here are the properties of hub and the nacelle. Again, like this is a direct drive turbine, so it has a gearbox ratio of 1. And yeah, the other parameters are provided. Again, this is a full aerolastic model, so it's almost like similar to how the NREL 5 megawatt model was presented. The details of the everything can be found out using the OpenFast files that are provided with this model. And finally, the control system. So a simple lookup table based torque controllers is employed. Of course, we don't have a pitch actuator here, so like no pitch controller, but the controller can be seen in this plot where, above a certain rotor speed, the torque increases to track the optimal tip speed ratio. And after around 150 RPM, which is the rated RPM of this turbine, the torque increases so that the RPM is tracked at the rated RPM of 150 RPM as the wind increases. And again, you can also see that this is a stall regulated turbine. So as the wind speed increases, you see that after a certain wind speed, the turbine power drops and the turbine stalls, and this is how the overspeed protection has been implemented. And this like continues for a while. So that's the control system behind this model. It's a simple lookup table based controller, but I think it's quite effective in maintaining rotor speed and providing like overspeed protection. So this was the NREL 15 kilowatt model, which was based on the Bergy XL15. I'm also going to talk about the NREL 20 kilowatt model, which is based on the QED Phoenix 20 turbine. And again, this is an active yaw. This is an active yaw turbine. So we have like a yaw controller implemented in there. This is slightly larger with a rotor diameter of 12.3 meters and a lower RPM of 78 RPM. Right. Again, like I have like all the details of the structural properties of the blades. I think like the important thing to note here is that the structural damping for all the modes, they were slightly higher with this model. So 3% for both the flapwise modes and 5% for the edgewise mode, which is slightly higher, but like that's the value from the that corresponds to the QED model. So that's what we are using. The aerodynamic properties, this turbine uses NACA airfoils, the NACA airfoils, and we have 3 different airfoils, and they have been implemented using simple polars. Those are provided with the turbine. I should have like 3 labels here, but there are like 3 airfoils that are used for this turbine. We have the blade chord and blade twist distribution. And the tower is a cylindrical monopile it is a tapered tower, so it has a diameter of 1 meter at the root and reduces to 0.75 meter at the tip. And I think the tower is around I forget the number, but yeah, I should have had like tower height here, but yeah, I think that's included in the model. We have mass density and stiffnesses. And again, we have like hub and nacelle properties. This is again a turbine with a gearbox ratio of 1, direct drive. This has like quite a heavy nacelle compared to the previous turbine. So, this is quite a bit different from the previous turbine. This is like slightly larger and again, active yaw. So of course, all this weight gets included in the nacelle weight. Yeah, and the controller, this is a lookup table based torque controller, but this is implemented using Rosco toolbox. But again, like in this turbine, the shutdown is taken care of by Rosco. And we have a lookup table based generator torque, which is, again, similar to the previous model, where the torque increases to track the tip-speed ratio, and above that, it tries to keep a constant rotor speed. Of course, it increases slightly, but if the wind speed increases by increases further, then the turbine shuts down, and that is how the controller has been implemented for this turbine. And again, so both of these turbines have been made available publicly on the NREL's GitHub page. That's available here. So we have the NREL 15 and 20 kilowatt. We are working on the NREL 90 kilowatt, and that's going to be up there soon. But we have these two models available on the NREL GitHub publicly, and I'll drop a link to this repository in the chat. But yeah, we have these two models, and the third one will be available quite soon. So this will cover a wide range of or like certain ash types that the distributed wind turbines have, and this should provide good references for further research. Yeah, that's it from me. Let me know if you have any questions, and I'm going to drop the link in the chat. Brent, I think you might be muted. Or is it me?
Can you hear me now?
Yeah.
Thank you, Ebony. Appreciate you presenting those and all the work you and your team have done on building those turbines and exercising some of those new capabilities. So we're going to move next to the AC/DC tool, automated Campbell diagram capabilities. And the lead for this is Derek Slaughter. Hello, Derek. And thank you for showing us what you've been doing on the AC/DC.
Sure, thank you. Let me share my screen. Maybe. Come on. Oh, there. Right. Just a second, guys. Some slight technical difficulties.
No worries. We'll get it. What's it doing? Nothing?
Oh, I had to give it permission. Can you guys
Okay.
see it now?
Yes.
Okay, great. Hello, everyone. I'm here to talk about AC/DC, a code to generate Campbell diagrams. I worked on this with Sora over the past year. So what is a Campbell diagram, or what is AC/DC? It's a GUI app that automates the generation of Campbell diagrams. And a Campbell diagram graphically relates the rotational speed of the rotor to the turbine's natural frequencies and damping, and generates plots like this. So AC/DC is a automation tool that you can use to import an OpenFast model, create a bunch of settings to perform linearization. The user gets to define like the range of operating points, wind speeds, rotor speed, blade pitch. It then generates OpenFast input files and runs all of the simulations in parallel, and post-processes the results, loading the linearization files, running the eigenanalysis, and then does a modal identification to connect similar modes across all of the operating points, and finally generates and displays the diagram. What are the advantages of AC/DC? The existing methodology involved a whole lot of Python scripts and manually setting things up in OpenFast. And this one provides a nice graphical user interface for performing the same analysis. It has a few new methods for connecting the modes and doing the mode identification. It also provides, the diagram is interactive. You can use it to like click on and explore the operating points and the associated modes. And finally, it has a nice capability of doing 3D visualization of the modes as seen over here. How do you get it? It's available on GitHub. There's several releases, recommend using the latest one, and there is some fairly complete documentation available on the GitHub pages, which looks like this. So you can download it here, which will take you to the releases, or read the documentation, all the various sections. And the download is like this. Expand assets. Binaries are provided for Linux, macOS, and Windows. Download those, they should just run. If they don't, please file an issue. We're happy to make things better and improvements. If you have any suggestions, feel free to document them here. So I'm going to show you guys a demonstration of the tool in action on the NREL 5 megawatt, and then maybe if we get to it, the QED reference turbine that Abinit was talking about. So I've got some pre-made model files. They're also in the repository for this for examples. But the essential process is you can create a new project file, import the OpenFast models, which looks like this. You go and you find the .fst file, the main OpenFast model, and it will import all of the associated files from there. Here's the list of files. If it doesn't import all of them, check your file paths, but it should grab everything that's relevant. Then you come down here and do linearization quick setup. There's a handy dandy defaults button that will change a lot of the basic settings so that you can just move forward with doing the analysis. But we're setting things like the output format to have sufficient number of decimal places, turning linearization on, calculate steady on, trim tolerance, some damping. Want to do 36 linears. We want to linearize at 36 points through a revolution of the rotor after it reaches steady state. And then there's just some basic settings that the user may want to tweak while they perform the analysis that are kind of easy to get to. You can also come down here and edit a whole lot of the settings in the files, the ones that are probably relevant to linearization, turning things off and so on. Next up is to set up the analysis. I've got a couple in here, one for structural only and one for structure plus aerodynamics. For the structural only, you specify the min and max RPM and the number of operating points, and then provide a curve of rotor speed versus blade pitch. This is pretty simple for the 5 megawatt reference turbine. Just doing a straight line essentially. For the structural plus aero, you need to have wind speed, rotor speed, and blade pitch, and define the cut in and rated cut out wind speeds. These boxes up here, below rated and above rated, have to do with using the controller to tune model parameters in order to make the model match the target rotor speed at the given wind speed. And you can see here, this is kind of what the curve looks like. The X's are the points input here, and then it performs a spline fit of those and interpolates to get the actual operating points so that you don't have to do manual interpolation. If you're not a big fan of typing these in one by one, because nobody is, you can import this table from a CSV file, and there's instructions in the documentation on how to format that. All right. Next part, I'm going to go ahead and start this, and then I'll talk through it because it takes a moment to run. You point you tell AC/DC where your OpenFast executable is located. you can get OpenFast from either Conda installation, compiling it yourself, or if you're on Windows, downloading it from the OpenFast releases. But this is pretty straightforward. You just browse for it on your local machine, and it will do a quick run and give you the information associated with it, so you know what you're running. What I did down here was I selected the case that I wanted to run, whether structural or structural plus aero, the number of CPUs to use in parallel, and then hit start. And as you can see down here, it's running through the simulation part and then through the linearization part. So once it starts doing the linearization, the simulation jumps to 100%. If something goes wrong, it will cancel all of the evaluations and say error right here. In which case you can click on the log button and it will show you the log output from running OpenFast. So you can use that to debug things and go back to the model and tweak parameters and come back and run until everything runs successfully. So you get this nice string of completes and everything's at 100%. Then we can jump to results, go over here to the current case. I've had already run this, so it had a bit more information here already, but the normal process is to click process on the linearization files. And then you can look through and see what the data at each operating point was. For this particular model, operating point 3, we found 14 modes, these natural frequencies, damping ratios, and so on. And then the next step is to click generate on the Campbell diagrams. And so this will give you the natural frequency versus rotor speed and the damping ratio versus rotor speed in RPMs. Since this is a structural only case, everything is versus rotor RPM. And so if I select like a particular point off of the diagram, I can come down here and there's a line label and a color, and the information about that mode. So what is the natural frequency and damp frequency and so on. So you can click around through here and explore what's going on in the model. But the most exciting part is to be able to visualize the mode shape. Set the visualization scale here and click visualize and scroll down and it will show you the shape of that mode. Let me set that scale just a little bit higher. So you can see the blades and the tower. Tower's not really moving, but the blades are wiggling back and forth. And that looks like a blade edgewise regressive mode, just based on the motion of it. You can then turn on the node paths, and that shows you the nodes on the blade, the path that they're taking throughout that mode oscillation. And so once you've kind of figured out what that mode is, you can come down here and say edgewise regressive, and it will include that information in the legend for the plot. You can also just click on line here and it will take you to the first point. Come down here and select any of the other points in that line and also do visualize. And you kind of have to play with the scale a little bit because the lower frequency ones don't need quite as much scaling, but here you can see a tower side to side mode and all the associated node motions. Something else that's kind of nice with this tool is you can fix errors in the mode identification. What we have here, let's see, visualize. So that looks like a collective edgewise mode. And if we look at the next point down here and visualize it, that looks more like a flapwise mode. And what's actually happened is that it has misidentified the mode as it went from this line to this line. And you can take and click that and then click the line that you want to swap that point with, which I believe was the line 4. 4 swap. And that you can use that to clean up your Campbell diagram so that you get the same mode all the way through all the lines. Another way to do that is this kind of experimental feature called spectral clustering, which will try to automatically clean this up using a method called spectral clustering. And there's information about that in the documentation. It works some of the times, but it also has the potential to mess up other identified lines, as you can see happened here. But yeah, so that is how to use the AC/DC tool to get a Campbell diagram and then visualize the mode shapes. Right, any questions?
Awesome. Thank you, Derek. Well, that's fun to watch. Any questions on AC/DC before we move to VOT modeling? Awesome. Well, thanks again, Derek. That's a lot of work in there, and a very cool output, and hopefully it's very beneficial or useful to folks trying to do their modeling and generate Campbell diagrams. So thanks again. Okay, so next we'll go into VOT modeling, vertical axis wind turbines, led by Kevin Moore and at Sandia, and then at NREL, on the NREL side, Hannah and Andy worked with Kevin on this. So take it away. Thank you.
All right, yeah, thank you for that, Brent. So on the VOT modeling side, we're right in line with the overall dWAM goals for improving the models, creating, helping with these reference turbines and doing the validation, improving the user experience, and realizing these impacts. And so, the motivation of this is that, for the vertical axis wind turbine community, they're, despite the historical failures from the 80s and 90s, and other aspects, that there continues to be both industry investment and companies that are pursuing new and innovative designs. And along with this IEA Wind Task 41, that it was identified that for wind, distributed wind in general, as well as for vertical axis turbines, that design and optimization and the use of these aerolastic tools is critical. And so our program has gone over 3 areas. And so in three years, in FY23, it was on research and development. We gathered a lot of industry feedback, engaged with certification bodies. We did a lot of work on the open fast library coupling so that we could get the higher order aerodynamics and some of the and better coupling for the turbulent inflow. This past year, we did a lot of the implementation for automated design, load case, pre-processing, and automated build, so that you can run an end-to-end solution that automatically generates all of the sectional properties and all of the post-processing, so that you can do design load case sweeps. And also the code was released in the open source domain. For this year, we'll talk more about this, but there's plan for validation and refinement of the models. So when we're running Owens, there's 2 aspects. There's the Owen side, which is we can run simplified aerodynamics and structures, and then there's also the open fast coupling that adds added features. And I'm going to talk specifically about the Owens features and improvements that have been done so far. And so, again, the code is out in the open source. It's been at Sandia for upwards of a decade, and we finally were able to get it open source. So a major thing that we're able to do for the industry. And then we did significant improvements for the robustness and the developer architecture, so that there's automatically deployed documentation and example cases, doc strings, testing scripts, and there's that automated pre-processing and post-processing so that we can get what we need for the design load case sweeps, and it minimizes the amount of post-processing manual work that you have to do. Additionally, we've added other modeling options and the ability to do advanced visualization, and added example cases and standardization of a lot of the internal building blocks that were being used, and as well as enabling a precompiled binary process that we hope will be able to simplify installation in the future. And so that's sort of a summary of work that's been done for dWAM on the Owens side. And so now I'm going to pass it over to Andy Platt for the work on the open fast coupling.
Yeah, thanks, Kevin. Yeah, as probably interested to know, I'm Andy Platt. I've been with NREL off and on since about 2011. I took a short break between 2016 and 2019 to go to Envision Energy, where I was part of the Blade Innovation Center, and then returned to NREL, where now I lead the integration on the OpenFast modeling software. We've tied, as part of this project, we've tied a couple of the OpenFast modules into Owens to be able to leverage some of the capabilities within them. For example, we've tied Aerodyne into Owens so that we can model using a free vortex wake method. In that integration, there's a module within Owens called this Owens OpenFast wrapper. And there are several improvements that were made within this wrapper, including automating the installation of the OpenFast libraries because they were somewhat difficult to install prior to this, automating some of the generation of the Aerodyne input files in order to make those a little easier for an Owens user to be able to use those. And then as part of this coupling, we're now able to model arbitrary blade shapes and different strut angles. And if you want to click next, here's a visualization of a couple of different turbines. And you can see in the upper right, we've got a vertical axis turbine. I believe this is the Sandia 5 megawatt. And on that, there are a couple of struts that are also aerodynamic airfoil shapes that are interacting with the wakes of the main blades. So with the OLAF, which is our free vortex wake calculation within Aerodyne, we can also model the interaction of wakes between multiple different turbines. So Owens will simulate two turbines like in the lower right corner here, and then the Aerodyne module that's coupled in will then simulate the interaction of those wakes between the two turbines. Other features that have also been added is the streamlining of the TurbSim and the inflow wind coupling for use within design load cases. We've also included several numerical improvements, and there are some updates that will be coming in the future. The Aerodyne inflow library, which is coupled in, does not currently support tower loads, but that is something that will be added in the next quarter as a part of another project, but will also, as a result, be incorporated into this Owens coupling.
Awesome, thank you.
One other thing I do want to mention, going back to the tail fin and the off friction models, those will be available in our OpenFast version 4.0. We expect to release that in the next, the early part of October. We expect to finalize our release 4.0 next month or next week, at the end of next week. So all these capabilities that we've been talking about will actually be out on version 4.0. Right, thanks.
Awesome, thanks, Andy. Yeah, so a lot of work going on here, and a lot of continued work in the future for this. So it's exciting to be able to leverage and synergize in these areas. So now I'm going to go ahead and go through a demonstration. It's a pre-recorded video, and it's accelerated. So in order to fit into the short amount of time that we have, I didn't want to have to have you wait through the installation processes. And so we're going to accelerate that so that we're going to go through why we chose the Julia language, and an installation and run of Julia and Owens. We're going to install and set up Visual Studio, as well as a design load case, run a design load case example, install ParaView and visualize that, run the automatic Campbell diagram analysis and visualize the modes, and a brief overview of the documentation, a showcase of some of the complex things that we can do, and then just a brief touch on the current status of the validation. So let me hop over to the video. So, why choose the Julia programming language? So I'm going to start off at the simulation in the background and note that, first off, it has all the benefits of an interpreted language that ultimately results in fewer lines to maintain and is easier, faster to develop. Second is that it has all the benefits of a compiled language so that it can be written as fast as C or Fortran, and it can be pre-compiled. There's also a lot of existing libraries in the Julia programming language for the structures, for the aerodynamics, and for a lot of the in-between components that are very useful for our use cases. And one of the important things that's interesting to me is the automatic differentiation. So we can do large-scale design optimization using the analytic gradients. And so like what was done in the background, where we ran a control co-design of a small VOT, aerodynamics only with what's the optimal chord and pitch control. So a freeform full pitch control at each one of the tip speed ratios to maximize the CP curve. And so 51 design variables, and it was enabled with these analytic gradients and using these open source modules in this environment. And so Owens itself was originally written as an analysis code as opposed to an optimization code, but we've made significant progress, and especially on a lot of these sub-modules like the aerodynamics only. But the overall ontologies is we're still working on bringing these advanced optimization capabilities to that. So now we're going to switch over to the overall Owens Aerolastic code that can be used for certification in the design load cases. And so in this demonstration, there's a couple of assumptions. First off, just accelerate this video that the installation instructions were read, your system can already install and compile OpenFast. You have the SSH key set up and your environment variables are already set up. The details matter, and there's a lot of instructions, and the details are in the setup instructions. So let's download and install Julia from Julia Lang. This installation is done on a Unix machine. It's on a Mac or on Linux, and so we can take advantage of the terminal and the package managers. And so there we ran the Julia installation. The installation's a little bit accelerated in the video, but so there Julia is installed, and now we're going to go and grab Owens, the Owens installation commands. And so we're going to go to the Owens repository into the documentation and grab these installation commands that we're going to drop into the Julia REPL. And that sets up all of the custom dependencies for Owens and precompiles. And so now within the main Owens repository, there's the example cases and the test cases. And so we're going to clone that locally so that we can run those. So clone that, and now we're going to make sure that we have all the dependencies at the top level. Julia has its package manager firewalls dependencies at different levels. And so when you want to run it at the top level, you need to make sure that it has those. But if you didn't do it, it would prompt you to install those. And so now we're going to run the test cases. So there's on the top level Owens, there's unsteady, there's modal analysis, there's some other checks as well. And all of the repositories, all those custom dependencies, they also have their own test cases as well that can be run using the package manager. You get into that in Julia with a backwards bracket, and you can tell it to test a certain package. All right, so now we're going to set up a Visual Studio Code as an IDE, so we don't have to run everything from the command line. So we're using the brew package manager. You could use apt-get if you were on Linux. And so that's set up. So now that's installed. Now we're going to open it, and then we're going to use the Visual Studio Code profile that sets up the Julia environment, all of the syntax highlighting, the debugger, etc. And so in Julia, when you run with the debugger, it acts as an interpreted language, but it's on the back end, it's compiled. And so you have to set up the debugger so that it doesn't step through every single little piece and take forever. And so that profile that's given, it speeds up and sets things up very nicely. So now we're going to run one of the examples that's shown in the documentation. This is the first simplest example, which includes a run DLC, the automated DLC run script that runs an end-to-end design load case. So we'll change the local path to match our system path as opposed to the documentation, and then we'll run that. And so that ran, that's great, but now let's install ParaView using the package manager, and then we'll open up ParaView and look at the ParaView output files. So this particular case, it ran with the Aerodyne Olaf aerodynamics, and so we load the ON structural side, and then we load the aerodynamics from Olaf. I didn't choose the right files, but I will on the next round. So now we're going to run one of the other cases where we're going to change a couple of things and have it run for a little bit longer. And so this is example B. We change those, run it for a little bit longer. The design is low to the ground, which is why the vortices are down there. We reload the files, and I selected the right files in between. And so now everything's all lined up. And so this architecture can be used either with a higher order aerodynamics, so you can get like the strut influence, or with a lower aerodynamics, lower order that's faster, and you can do all of the design load cases and a wide variety of designs, configurations. Here's an example of a torque paper that was published recently where we went through a course sweep of all of the design load cases for an HVAC. All right, so one more thing, I'll show the Campbell diagram. So this is part of the test suite. So we're going to uncomment the plotting scripts, and so that they'll run, and then we're going to run it. And this, on the Campbell diagram generation, it runs the Timoshenko beam element theory as well as the geometrically exact beam theory, and then we compare it against the Sandia 34-meter legacy data. Now let's open up ParaView and look at those modes. And so we've got just these are what happen to be saved. So we've got modes 1, 3, and 5 at different RPM levels. So this would be analogous to the structural only, as VOTs are primarily driven by the centrifugal loading. And so, there's mode 5, and then we can look at the different frequency. And so the ParaView is great. There's still a lot of work to do, and there's also significant documentation, still more work to do on the documentation, but we've got these example scripts. We've got the API reference with all of the inputs and outputs for the functions. Not perfect, but there's a lot there. Also, ONS there's a spectrum of what it can model, and so when you use those fundamental building blocks, they're very powerful, and you can model a very wide variety, such as this the Windward Engineering Blade Runner concept, where we want to do the spokes, and we can run the full aeroelastic simulations with that. And then on the other side of the spectrum, where you want to just run with a black box and you just want to be able to run more classical or canonical cases, we're doing significant improvements on that to be able to do that in this year. And then this year we're doing a lot of validation. We do have confidence in the design, as we've done validation against this 34-meter turbine. It's a 500 kilowatt, but it's aluminum, and it was from the 80s and 90s. And so we have confidence in the implementation, but we're really excited to be able to validate the existing composite input and all those sectional properties, and propagating that all the way through for FY25. So really excited. A lot more to come on user improvements as well. And so that's it for the video. So now we should have some time at the end for questions or comments. But I'm going to pass off to Hannah for our current roadmap.
Thanks, Kevin. So my name's Hannah Ross. I've been a researcher in the NREL water power group for about 4 years. So again, background mostly in water power, but I've worked quite a bit with cross-flow turbines, which have a lot of overlap with VOTs on the wind side, as far as their operating conditions and physics. And so it's been fun to come into wind and do some work with VOTs on this dWAM project. So like Kevin demonstrated, ONS is released. It's ready to be used for VOT modeling, but there are some refinements that we still want to make. And ultimately, kind of the goal that we want to have, or the goal that we do have for this software, is for it to be able to be used by industry for certification, feasibility assessment, and design and nonlinear optimization. And so we want kind of all of these three kind of important targets to be met by this code. And we want this additional flexibility to be able to perform these or achieve these for various different types of VOT archetypes. As you all well know, the VOT industry hasn't converged on something that looks similar across the spectrum. There's lots of different designs and geometries out there. These are just representative of some of them, but these are all models or geometries that can be modeled by ONs. And so we want to continue to refine the model for these various archetypes and make sure that we can get accurate results that are needed for all of these tasks. So what we have planned for the next steps of this work is, again, validation of these different common archetypes. And that includes some internal accuracy improvements, so kind of digging down into some of those submodels and getting as accurate as we can with specific component and submodel validation. We also want to continue to do industry engagement. Can you hear me still?
Yes.
Yeah.
Yeah. Yeah, so we want to continue to do industry engagement to make sure that we're going, in the direction that is most useful. And with that, we want to enable easy uptake. So we want to make sure that the ease of use of the code and documentation is there to really make sure that this code can be adopted and used as easily as possible. And then we also think that there's a good opportunity to provide some feedback on the IEC 51400-2 for small wind turbines. There's not necessarily built-in consideration for all the different types of small markets. So I think there's a good opportunity using the code and all these different geometries to be able to provide feedback to that standard. And like we have in the top of the slide here, we are very open to and encouraging of any feedback that you have on this roadmap to make sure that our goals are aligned with what's most useful for you. Thank you.
Awesome. Thank you, Hannah. So yeah, so that concludes our the VOT portion. We might have a few minutes now for feedback and or questions, and if not, then we can hand it off to the end of the webinar.
Awesome. Thank you, Kevin and Andy and Hannah. That's great work on the VOT world. Again, for folks that can't be here, we're going to post the recording and spread the word and access a few more folks in the industry. So thanks for all the work there and for presenting it in an accelerated fashion. Okay. So next, almost to the end, we'll just get an update from Rick Damiani on a document that we're working to publish now, giving some design load basis guidance. So back to you, Rick.
Yes, thank you, Brett. So I'm talking about the design load basis guidance for distributed wind turbines. This is a document that I worked on with Dean for several months. We put a lot of effort into it, and we're really excited about it. As much as you can be excited about a document like this, but it's we think it's a great guidance document to create what is called design load basis. The motivation again came from the results of that investigation we mentioned earlier on, where stakeholders expressed a general concern about the complexity in the generation of numerical simulations and the extraction and post-processing of the results to advance their design as well as the path to certification. So the DLB obviously is also a tool that can be used to support both the design within a group of engineers, but it also helps towards certification. So it's not supposed to be fully standalone. It requires some interaction with a CBA or a certification body. And you can see here a number of logos that I picked from some that I worked with in the past in a way or another. And more guidance can be found under the operational documents issued by IECRE. So what are the main contributions of this technical report that we're about to publish? I would say first and foremost, we really formally describe the scope and the role of the DLB. So again, the design load basis within the context of the larger design basis and within the context of the certification pathway. We've also produced a typical table of contents that can be used by a typical user or a typical stakeholder. And we've provided a very detailed description of the various sections as well. This document also provides a list of relevant design standards, both for certification as well as for design guidelines. And we try to fill in the gaps that exist in the main design standards for distributed wind, in particular, those in -2, 61400-2. We've also provided a real-life example of a DLB, including what we call the LCT, or load case table, which is an instrument that you can use with the CBA or your certification body to vet your design strategy and your aerolastic modeling philosophy, if you wish. And we'll talk a little bit more about the LCT later in this presentation. Also, we propose some methods for post-processing of the limit states, the ultimate serviceability and fatigue limit states. And I think that actually is one of our major contribution right there that could potentially make it into a new revision of the standards later on. We've also touched upon additional guidance on other items of design, certification, and verification and validation. I don't see you guys anymore here, but I hope you guys are still online.
Yeah, we're good, Rick. Thank you.
Okay. So where does the DLB fit within this path to certification? Well, as you can see here, we start from the design basis towards the design evaluation, all the way to a design certificate, a type certificate potentially, so a conformity statement released by the CBA. Well, the design load basis feeds into both the design basis and the design report. So both in the design basis evaluation as well as the evaluation of the design per se. So it's a very fundamental piece, if you wish, of the design basis, and we try to formalize it. And by formalizing it, we actually make it simpler. A lot of the guidance may come from, again, from the operational documents 501 and 554 of IECRE. And again, the users are encouraged to peruse those documents as well. Here's perhaps the main content of the DLB. The DLB really provides specifics related to load calculation and component verification. It provides the methods and not the results of the load calculation. The results obviously go into a design report, but it provides the constraints within which you can drive your design. It also provides a hierarchy of standards that you would be using for your design, and the system of units, the coordinate systems, load channels, and nomenclature that may differ from the standards, for example. It also provides details of the aerolastic model or the software and the various methods that you may be using to calculate your loads and then to do your post-processing, really. One other aspect really important of the DLB is the technical description of the turbine, including the potential faults or failure modes, and the relationship between those and the DLCs that you would be simulating. Of course, it also includes the analysis method for post-processing, including partial safety factors, environmental conditions, obviously, and the fundamental LCT, which is this load case table. Here's an excerpt of this report that shows the table of contents for a typical design load basis. So as you can see here, the various sections span from the description of the project to the numerical model description, all the way to the reporting requirements. So, it's good practice to put in writing what you would be delivering in your final design report, and sharing this document, the DLB, in advance with the CVA goes a long way, as it allows them to vet your DLB, to vet your LCT and your procedure, and also that, say, the outline of the report that you will be providing. So again, this requires a little bit of effort up front, but it allows you for a smoother transition, a smoother interaction in your search for or request for certification. We provided a very detailed description of the various DLCs, and we filled in a lot of the gaps that exist currently in -2, primarily with information coming from -1 that is much more complete and thorough. For example, we specify for the various DLCs how many runs, how many seeds, how long the simulations should be, and what kind of parameters in terms, for example, of yaw offsets, besides the environmental conditions to use. We also specify very clearly what kind of partial safety factor you would be using and how you would go about doing, say, the averaging of the various results. And here is the load case table, or LCT, which is the fundamental piece of the DLB that again can be used to interact with the certification body. It contains a list of the cases specifically for your turbine model, for your configuration. That means that some cases may be omitted for some reasons, and so you can demonstrate, obviously, with some narrative why those cases are omitted, or why certain parameters within certain DLCs have been chosen. And by the same token, here is where you make that connection between the faults that may happen in your system with what you're going to actually simulate. And again, this is usually very vague in the standards. There's just one sentence about how to do that, and we went into a lot of details on how you can organize this to have a very thorough assessment of loading levels associated with fault conditions. So again, here you can see we have different columns where we have the design load cases for different design situations, and then a description of all the environmental conditions, the number of wind directions, the number of seeds or turbulent wind seeds that you would be using. So an assessment of the length of the simulation and the number of simulations, so the product of those two. and the type of assessment, whether it's going to be for ULS, FLS, or serviceability. We also provided a lot of guidance in the post-processing that can supplement, again, what's already in the standards, but with some more practical examples, perhaps, on how to really put together the results. For example, for the ULS and SLS, we talk about the Campbell diagram. I don't have to spend time on that, thanks to Derek in his presentation earlier. But we discuss how to create a simultaneous load table. So what goes into the averaging of all the results to, in the end, extract an extreme case load table with simultaneous loads, and also how we go about handling PSFs within the context of the load resistance factor design approach. For fatigue, probably this is really new. I haven't seen this formalized like this before. So I think this is a really great contribution to the community here. This guide to FLS processing, we discuss how we go from load cycles towards not only DLs and Markov matrices, but really how we make the connection to both the DLCs and the lifetime that we expect for that particular turbine. So this table right here on the upper right really summarizes it in, I think, a very concise manner, but very thorough manner, how you go about taking care of the various DLCs to assign fraction of your lifetime. And yeah, without going into too many details, but you can read the report, but substantially by selecting availability and number of faults per year, depending on the types of faults and the number of shutdowns, then you can actually address the weight factors that you would associate to the results of certain DLC simulation runs to the individual or short-term DELs to finally calculate an overall damage for the entire lifetime. And this is very clearly explained in this document. And again, you don't necessarily have to follow this approach, but we think it's a fairly standard approach also with larger manufacturers, and it can be used in the DWT world. We've also expanded this treatment to the tower fatigue, which accounts also for wind directions. This is not necessary for the ACP certification, but it's probably good to have for specific installations. So for some of the stakeholders that are involved in the site suitability assessment, so the actual retailer, for lack of a better word, and installers and the developers, this is a tool that can help assessing whether or not a tower is suitable for a certain site. Like I mentioned before, we touched upon some other additional elements not directly connected to the DLB per se in a standalone fashion, but connected to the overall certification pathway and workflow. So we discussed the design procedure and the philosophy of control of design. Here on the right-hand side, you see a typical list of steps conducted in the design. So you start from a preliminary design of your turbine, you do your model analysis, and then you select the DLCs, you actually run those DLCs. And finally, you go into the detailed design and you assess the tower and the foundation somewhat in that order. And showing this again to the certification body can help a lot to understand who's doing what and whether or not certain things are not clear or require more due diligence. We also touched upon the FMEA, which it's another tool that is available to, I would say, to the engineers in general. This is the design failure mode and effects analysis matrix or table that allows you to understand what the failure modes might be and what the severity or probability of those failures could be. And then you can come up actually with a risk number. It's usually called RPN or risk priority number. And that not only lets you understand the priorities in terms of risks and failures, so the risk associated with those failures, but also it lets you prioritize your analysis. And this is where you make the connection again between failure modes, faults, and DLCs, and that allows you to really put those more abstract DLCs into a more realistic context. We also discussed other elements of BMV, but in the interest of time, I'll skip that. You may be bored enough already. So concluding, yes, we have identified the scope and the contents of the DLB in a very formal way, if you wish. We have provided detailed explanation of the various sections that go into the DLB, together with very thorough descriptions and a setup guidance for the aerolastic model typical simulation. We also provided in parallel, I haven't mentioned this too much, we provided this very real life template, very example of a 50 to 60 kilowatt machine that has been recently designed by myself and Dean. And we provided basically the typical sections that formed our DLB. We also provide a step-by-step guidance in the post-processing, as I mentioned, and the verification for the various limit states. So this is just suggested future work where we would put all these things that we discussed today into a package. So starting from the reference turbines that NREL and we've been working on, together with a design basis, a complete design basis, perhaps with a DLD. And then we could actually produce a full loads and performance report. So kind of a typical design report, at least for the loads. And then obviously what we really would love to do is some verification validation work with all the data that will be coming out of NREL. So with this, again, I thank you all for attending today, and I thank you, NREL, for their support and guidance in this project.
Awesome. Thank you, Rick. Thank you very much for this work. As this report is in the publication process at NREL, and it's going to go through a series of edits and reviews. And once it's published, we'll add it to the dWAM website. Any questions for Rick? Then we'll wrap it up with a few more bits. One on next steps. Let's see. So yeah, we've installed some turbines at NREL and hope to do some validation work on the tail vane controlled turbine behavior. We want to get some data from the Berge to do some validation work there. On the passive yaw friction validation, we've got the Berge and the EO-cycle turbine to do some experiments on for yaw dynamics, passive yaw dynamics validation against the new tools and capabilities. We are working with Carter on this downwind passive yaw archetype, and it presents a verification opportunity to compare the modeling of this turbine in OpenFast and in bladed, because it's been modeled in both. On the AC/DC side, we've got the QED or the EO cycle to do some modal measurements on the actual turbine, maybe the blades and tower compared to what the model is putting out for an output for validation of that tool. And then, in the course of building the reference turbines and looking back at, I think, one of Rick's first slides, controllers are challenging in OpenFast for stall controlled turbines. So I think Ebonite's going to do some work on a controller to be used for these stall controlled archetypes in OpenFast. And then on the VOT side, Kevin can speak to this.
Yeah, we've talked a little bit about this in the previous slide. Some details about this. There's specifically for tower cable model validation, sectional property model validation, validation against a Darius turbine, the Shava, and as well as completing the X-Flow HVOT validation, and as well as improvements and verification on the post-processing for the fatigue and a finalization of this WindIO common file-only input run option, more improvements on the documentation and industry engagement and bug fixes.
In general, I mean, we knew this, but we got some good peer review feedback in our recent peer review of this project for the Department of Energy that it's really, really important to help the distributed wind industry understand how to access, set up, utilize all these new tools and capabilities. So we want to focus on that this year as well. Recording, publishing instructional texts and videos targeted toward modeling efforts of these tail vane, yaw, friction, passive yaw archetypes, generating camel diagrams and modeling VOTs. So if you have, if folks have specific needs, specific questions, we're available and we want to be helpful. We want to put out any helpful documentation or assistance that will help you implement these new tools. And we'll open it now to both ideas for any additional efforts or needs in this space and any questions you have here before we wrap it up today. So thanks again for attending. Let's see. So if you want to say anything, go for it. If you have a comment or a question, let me know. I think you can unmute. If you can't, I'll make it so you can. Great. Well, again, we're gonna take all this great work condensed in a 2-hour session, post it to the dWAM website for further dissemination, and keep up the good work. Thanks again for attending. Thanks to all the speakers today and the whole dWAM team for working on these tools to support the distributed wind industry. And thanks for the DOE support for this project for NREL and Sandia.
Thank you, guys.
Thank you.
Thanks.
Thank you.
Thanks.
All right, have a good rest of your day and stay dry. If you're in the East, it's still raining here. And take care. Bye-bye.
Good luck.
All right, thanks, Kevin. We got it all in there. I can't hear you, but
Sounds good. I'll let you handle the recording and
yep.
Cool.
All right, thanks. That was great. I appreciate all your efforts there. That was really a lot of information. Take care.
Much in the time allotted.